On the night of August 15th, 1977, a volunteer named Jerry Eman sat down at a desk in Columbus, Ohio, and began doing what he always did, reading computer printouts of radio telescope data collected by the Big Ear Observatory at Ohio State University. It was routine work, the kind that requires patience more than brilliance, scanning columns of numbers representing signal intensity at specific frequencies, looking for anything that deviated from the background noise of space. And then he saw it. A sequence of characters in the printout, 6EQUJ5, representing a radio signal of remarkable structure, remarkable intensity, remarkable narrowness of frequency, remarkable duration. Everything about it was consistent with exactly the kind of signal that SETI researchers had been predicting for years an extraterrestrial intelligence might produce if it wanted to be heard. Eman picked up his red pen and circled it. In the margin he wrote a single word: wow. The wow signal has never been explained. In 47 years of follow-up observations, scanning the same region of sky at the same frequencies with increasingly sensitive equipment, it has never been detected again. It remains the most compelling candidate signal in the history of the search for extraterrestrial intelligence, and simultaneously one of the most maddening, because a signal that appears once for 72 seconds and then vanishes and never recurs is almost impossible to classify definitively. It could have been natural. It could have been terrestrial interference. It could have been something genuinely extraordinary. We don't know. We have never known. The wow signal came from the direction of the constellation Sagittarius at a frequency of 1420.405 MHz, the frequency of the hyperfine transition of neutral hydrogen. This frequency was not chosen at random by the signal, if it was artificial. In 1959, physicists Philip Morrison and Giuseppe Cocconi published a paper in Nature proposing that the 1420 MHz hydrogen line frequency would be the natural choice for any civilization attempting interstellar communication, precisely because hydrogen is the most abundant element in the universe, and any technologically capable civilization would know its spectral properties. Drake's original search in 1960 used this frequency. The wow signal appeared at exactly this frequency. The precision of the match, 1420.455 MHz, within measurement uncertainty of the hydrogen line, is one of the properties that makes it difficult to dismiss. The other properties are equally striking. The signal was narrowband, consistent with an artificial transmitter rather than a natural broadband source. It was strong, peaking at 30 times the ambient background noise level, a signal-to-noise ratio that would be remarkable even for a known pulsar or quasar. It lasted for exactly 72 seconds, the full duration of Big Ear's observation window for a fixed point in the sky, consistent with a signal from a fixed celestial source as the Earth's rotation carried the telescope's beam across it. Every feature pointed in the same direction. This was not noise, not a known natural source, and not obviously terrestrial interference. But here is what I want to tell you. The wow signal, as famous as it is, as persistently discussed as it is in every survey of anomalous astronomical phenomena, is not the story I'm here to tell you today. The wow signal is the backdrop, the context, the thing that happened in 1977 that set the standard for what an anomalous signal looks like, how scientists respond to it, and why the ones that resist explanation become permanently embedded in the scientific literature as nagging unresolved challenges to our understanding of the universe. Because in the years since the wow signal, and particularly in the last decade, as our instrumentation has become incomparably more sensitive, and our sky surveys have become more systematic and more comprehensive than anything Jerry Eman could have imagined in 1977. We have received signals that are, in specific technical ways, stranger than the wow signal. Signals that are not just anomalous in the sense of being unexpected. Signals that are anomalous in the sense of being specifically difficult to explain with any known natural mechanism. Signals that have generated genuine, sustained, heated scientific debate, not at the fringes of physics but at its centre, in peer-reviewed journals, at major conferences, in the offices of researchers at Harvard and Cambridge and Caltech, and the Parkes Observatory in Australia. Some of these signals are from objects in deep space, objects whose behaviour defies simple categorization, and whose emission mechanisms are still actively contested. Some are from closer to home, from within our own solar system, from surfaces and atmospheres that should, by every prior model, be electromagnetically quiet. And some are from places that are difficult to assign a location to at all because their origin is disputed and the dispute itself is part of the story. This video is about those signals, the real ones, the ones in the literature, the ones with published coordinates and measured frequencies and documented detection histories. We're not going to talk about UFO sightings or government whistleblowers or leaked documents. We're going to talk about peer-reviewed, reproducible, institutionally documented anomalies that have been studied by serious scientists and that remain, after serious study, unexplained. The reason unexplained signals matter, the reason they deserve careful attention rather than dismissal, is not that every anomaly is evidence of extraterrestrial intelligence or exotic physics. Most anomalies resolve into mundane explanations once the right data is collected. The history of astronomy is littered with phenomena that looked extraordinary and turned out to be ordinary, seen at the wrong angle or in the wrong frequency band or with insufficient baseline data. But some anomalies don't resolve. Some accumulate evidence rather than dissolving it. Some resist every proposed natural explanation with increasing specificity, such that the remaining explanations, the ones that haven't been ruled out, are themselves deeply strange, and it is those, specifically those, that are worth examining with both rigorous skepticism and genuine open-mindedness. The universe is under no obligation to be simple. It is under no obligation to produce only signals that fit our existing models. The history of physics is the history of signals that shouldn't exist by prior theory turning out to be the entry points into entirely new frameworks of understanding. The cosmic microwave background shouldn't have existed under 1940s cosmology. The accelerating expansion of the universe, discovered by a supernova survey team that expected to find the expansion decelerating, shouldn't have existed under pre-dark energy physics. Pulsars, when first detected by Jocelyn Bell Burnell in 1967, were so regular and so artificial-looking that her team called them LGMs, little green men, before the correct explanation, rapidly rotating neutron stars, was worked out. The pulsar story is worth dwelling on for a moment, because it is the most instructive historical precedent for what happens when an anomalous signal resists explanation. Bell Burnell was a graduate student at Cambridge when she noticed, in radio telescope data she was manually reviewing, a series of radio pulses that repeated with extraordinary precision every 1.3373 seconds. The precision was stunning, better than the best atomic clocks available at the time. No known natural phenomenon could produce such regular pulses from a point in the sky. The obvious question, whether the signal might be artificial, produced by an intelligent source, was considered seriously enough that the signal was temporarily designated CP1919 with the informal LGM1 tag. The hypothesis was not ridiculous. It was the scientifically appropriate response to a signal that fit the known signatures of an artificial transmitter better than any known natural source. The correct explanation arrived when Bell Burnell and her supervisor Anthony Hewish discovered 3 more pulsing sources in different parts of the sky. Multiple artificial sources all pulsing with similar properties, but different periods seemed far less likely than a single natural mechanism. The model that eventually fit, a rapidly rotating neutron star with a powerful magnetic field, sweeping its radio emission beam across the sky like a lighthouse, was itself something that had been theoretically predicted only a couple of years earlier and had not yet been observationally confirmed. The anomalous signal led directly to the confirmation of a new class of astronomical object. The lesson is not that every anomalous signal will eventually be explained by a new class of natural object. The lesson is that anomalous signals deserve sustained, rigorous attention, and that the discomfort of not knowing what something is should not be resolved by forcing it into an inadequate category. It should be resolved by understanding it correctly, even when that requires building new physics from the ground up. The signals we're about to discuss may resolve into mundane explanations tomorrow. New data may arrive, a new model may be proposed, a previously overlooked instrumental artifact may be identified, and the anomaly may dissolve. That is science working correctly. Or they may not, and if they don't, the implications, just for physics, for cosmology, for our understanding of what the universe contains, are genuinely profound. I want to say one more thing before we start, about the language of anomalies in science. There is a tendency in popular science communication to treat unexplained signals as either proof of something extraordinary or as embarrassing gaps quickly to be plastered over. Neither of these is the correct response. Unexplained signals are the most valuable objects in science. They are the places where our models are pointing at the universe and saying something false or incomplete, or simplified in a way that misses something real. The discomfort of an unexplained signal is the discomfort of being corrected, and being corrected is how progress happens. The specific signals we're about to examine have been studied by some of the most capable radio astronomers and theorists in the world, using the most sensitive instruments in history. They have not been quickly explained. They have not been dismissed as noise. They have accumulated evidence, spawned theoretical papers, generated international collaborations, and in several cases produced results that have genuinely changed the way physicists think about specific extreme physical processes. They are not fringe curiosities. They are anomalies at the center of active, rigorous, peer-reviewed science, and their continued resistance to explanation is itself a scientific result of significance. Let's begin. Chapter 1. Fast radio bursts. The signal that broke every model. Let's start with the phenomenon that, more than any other in recent astronomical history, has forced the scientific community to confront signals that should not exist by any prior model of what the universe could produce. Fast radio bursts, FRBs. The name is technically accurate and almost entirely fails to convey why they are extraordinary. A fast radio burst is a brief, intense pulse of radio emission, typically lasting a few milliseconds, sometimes as short as microseconds, detected at frequencies between a few hundred megahertz and a few gigahertz. They appear to come from extragalactic sources, from distances of hundreds of millions to billions of light years, and their intensity at those distances implies a power output that stretches the limits of what known astrophysical processes can produce. Let's start with the first detection, because the first detection is a story about how anomalies enter the literature, not with fanfare but with confusion, skepticism, and the slow accumulation of data that forces a problem onto an unwilling community. In 2007, astronomers Duncan Lorimer and David Narkovich, working with pulsar survey data collected by the Parkes Radio Telescope in Australia, found a dispersed radio pulse in archival data from 2001. The pulse had characteristics unlike any previously catalogued source. Its dispersion measure, a quantity that describes how much the radio signal has been smeared out by passing through the diffuse electron plasma of intergalactic space, was far too large to be explained by electrons in the Milky Way. The dispersion implied that the signal had travelled through an enormous column of intergalactic plasma, which meant it had originated at an enormous distance, an extragalactic distance. Lorimer and his collaborators published the detection in Science in 2007. The community was sceptical. Radio telescopes are subject to all kinds of terrestrial and instrumental interference. There was no obvious physical mechanism that could produce such a bright, brief broadband radio pulse from billions of light years away, and there was only one of them, a single event in archival data, with no way to verify it was real rather than an artifact. The skeptics proposed an alternative. The signal was produced by terrestrial radio frequency interference interacting with the telescope in some unusual way. Specific names were proposed for this class of fake signals. Perytons, named after a mythological winged stag, were identified as a source of FRB-like signals produced by microwave ovens being opened prematurely while running inside the Parkes facility itself. This was not a joke. It was a real discovery, published in a real paper that temporarily cast doubt on the entire FRB phenomenon. But the data kept coming. Over the following years, additional FRBs were detected, then more. The events had the same dispersion measure characteristics as Lorimer's original detection. They came from different parts of the sky. They could not all be microwave ovens. By 2013, a survey paper cataloguing multiple detections made the extragalactic origin hypothesis essentially unavoidable, and the community began, somewhat reluctantly, to accept that fast radio bursts were real, were extragalactic, and were something new. And then the mysteries deepened considerably. Because once the community was paying proper attention, the FRB started revealing properties that made the problem harder, not easier. The first genuinely paradigm-challenging discovery was the repeating FRB. In 2016, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, detected a source designated FRB2012110-2A that had burst multiple times from the same location in the sky. Previously, all detected FRBs had been one-off events, a single pulse, never repeated from the same coordinates. The existence of repeating FRBs immediately ruled out the most popular catastrophic source models, which assumed FRBs were produced by events that destroyed their progenitor. The merger of two neutron stars, for example, or the final collapse of a massive star. A repeater couldn't be dying. It was still there. It burst once, and then it burst again, and again. FRB2012110-2A was localized to a dwarf galaxy about 3 billion light-years away. Within that galaxy, it was pinpointed to a specific region associated with a persistent compact radio source, possibly a young neutron star in a turbulent, highly magnetized environment. This was a clue, but it was not an explanation. Neutron stars produce radio pulses. We know them as pulsars, and we've been studying them since 1967. But pulsars produce regular, periodic pulses with specific spectral properties. What FRB2012110-2A produced was something different. Irregular, enormously energetic bursts whose brightness temperature, a measure of the minimum physical temperature of the emitting region, derived from its luminosity and compactness, implied physical conditions that would violate known physics if you took them literally at face value. Here is what brightness temperature means and why it matters. When you observe a compact radio source and measure its flux density and its angular size, or infer its size from the duration of its pulse, you can calculate what the temperature of a blackbody emitter of that angular size would need to be to produce that much radio power. For fast radio bursts, these calculated brightness temperatures are around 10 to the power of 35 Kelvin. For comparison, the surface temperature of the Sun is about 6,000 Kelvin. The temperature of the hot intracluster medium in galaxy clusters, some of the hottest gas in the known universe, is around 10 to the power of 8 to 10 to the power of 9 Kelvin. The brightness temperature of FRBs exceeds this by 26 orders of magnitude. The reason this doesn't mean the source is literally at 10 to the power of 35 Kelvin, which would vaporize any physical object in most theoretical frameworks, is that the radio emission is not thermal. It cannot be thermal. At those temperatures, thermal emission would be in X-rays or gamma rays, not in radio waves. The emission must be coherent, produced by charges moving in concert, like a synchronized radio transmitter, rather than randomly like a thermal radiator. Coherent radio emission is produced by masers, by pulsars, by some forms of plasma instability. The physics of coherent emission at the energy scales implied by FRBs is not well understood. To appreciate the scale of what we're talking about, a typical FRB releases, in a few milliseconds, the equivalent of the total energy output of the Sun over several days to several months. All of it, in radio waves, in a few milliseconds, from a region of space no larger than a few hundred kilometers, across, the size of a small country. The energy density in the emitting region, if the source is as compact as the pulse duration implies, is staggering. No thermal process at any known temperature produces this combination of energy, compactness, and coherence. We're observing a physical regime that has no clean analogue in any setting accessible to terrestrial experiment, and whose mechanisms we are inferring from electromagnetic signals that have travelled billions of light-years to reach our detectors. This is not a minor theoretical puzzle. It is a fundamental gap between our best astrophysical models and observable reality. When a signal that should not be producible by any known physics arrives at your telescope with perfect repeatability and statistical consistency across hundreds of detections, the honest response is not to shrug and say it must be magnetars. The honest response is to acknowledge that if it is magnetars are doing something our physics doesn't fully account for, and that the gap between what our physics predicts and what the universe actually does is the most interesting place in science. By 2022, CHIME had catalogued hundreds of FRBs. The telescope's wide field of view and continuous sky monitoring made it uniquely suited to building large statistical samples, and those samples revealed a population of sources with a range of properties, some repeating, many apparently not, some with complex subpulse structure, some with periodic activity windows, some with polarization properties suggesting extreme magnetic field environments, some with none of these features. In 2020, CHIME detected an FRB from within our own galaxy, from SGR 1935+2154, a soft gamma repeater and magnetar, a neutron star with an extraordinarily powerful magnetic field, located about 30,000 light-years away. This galactic FRB was weaker than extragalactic ones, as expected from the distance scaling, but its properties were otherwise consistent with the extragalactic population. This was significant because it linked FRBs to magnetars, providing a plausible source class and a mechanism, though the specific mechanism by which a magnetar produces coherent radio bursts at FRB energies is still debated in the theoretical community. So, magnetars as a leading explanation, plausible. But here is where the anomalies within the anomaly begin to accumulate in ways that make the magnetar hypothesis feel incomplete. The repeating FRB 202011248A, detected first by CHIME and subsequently studied in extraordinary detail by the 500-meter Aperture Spherical Radio Telescope, FAST, in China, the world's largest single-dish radio telescope, produced bursts with an intricate internal structure that nobody had predicted. FAST detected more than 1,800 bursts from this source in about 47 days of observation. Within individual bursts, FAST-sensitive measurements revealed quasi-periodic substructures, oscillations within the burst envelope that repeated with a period of around 217 microseconds. These substructures showed complex polarization behavior, with the polarization angle varying in ways that suggest a rapidly rotating emission source in a highly magnetized environment. Here is the thing that should make you pause. A 217 microsecond period corresponds to a rotation rate, if the substructures are produced by a rotating emitter, of about 4,600 rotations per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates at 716 revolutions per second. FRB 202011248A appears to involve an emitting region, rotating more than 6 times faster than the fastest known pulsar, if the substructure periodicity is interpreted as rotation. This doesn't necessarily mean the rotation interpretation is correct, but the alternatives are also not obvious, and the theoretical community has not converged on a consensus explanation for the substructure. Then there is FRB2 0220912A, detected by FAST in 2022 and published in 2023 in Nature Astronomy by a large Chinese collaboration. This source produced 1,863 bursts over a 264-hour observation window, an unprecedented dataset. The bursts showed a pattern in their frequency drift, the way the burst emission shifts in frequency over the duration of the burst, that was consistent with a specific theoretical prediction about drifting sub-pulses in rotating sources. But the energy released in individual bursts, and the total energy budget of the entire burst, storm, strained even the most energetically favourable magnetar models. A specific paper published in 2022 by Micheli, Hessels, and collaborators analysed the polarisation properties of repeating FRBs and found that some show 100% linear polarisation, something that is physically possible but that requires specific geometric and magnetic field configurations. Others show rapid swings in polarisation angle within a single burst, suggesting passage through a rapidly changing magneto-ionic environment. The diversity of polarisation properties across the population suggests that either there are multiple source types masquerading as a single phenomenon, or a single source type that produces a wide variety of emission behaviours depending on environmental conditions that vary from burst to burst. And then there is the mystery of the non-repeating FRBs. The vast majority of detected FRBs have been observed only once. This is partly a sensitivity and cadence limitation. CHIME doesn't stare at individual sources continuously, and a source that bursts once a year would appear non-repeating in any reasonably short survey. But there is a statistical argument that some of the apparently non-repeating sources genuinely are non-repeating, that they were produced by one-time catastrophic events whose progenitors are destroyed. If so, the FRB population contains at least 2 physically distinct source types. If some FRBs are produced by magnetars, and some are produced by cataclysmic mergers, why do they look so similar? Why is the dispersion measure distribution, the brightness distribution, the spectral properties of the two populations so consistent? These are not questions that have settled answers. As of 2025, the FRB field is one of the most active and most contested in observational astronomy, with models that range from straightforward magnetar in turbulent environment scenarios to much more exotic proposals, including at the fringes of serious discussion, one paper that was published in a peer-reviewed journal in 2017 and proposed that some FRBs might be produced by artificial beamed light sail propulsion systems of technological origin on the grounds that the energy and spectral properties were consistent with a radio frequency leakage signature from an enormous transmitter-powering spacecraft. That paper was written by Manasvi Lingam and Avi Loeb at Harvard. It was peer-reviewed. It was published. It was not the author's preferred explanation. They were explicit that natural explanations were more likely, but they demonstrated that the hypothesis was not ruled out by the data. That a published paper in a reputable journal can seriously consider technological origin as a viable, not yet excluded possibility for a signal class is itself a statement about how genuinely strange the signals are. The FRB field has settled into a working consensus. Magnetars are probably responsible for at least some of the population, while simultaneously acknowledging that this consensus is incomplete, that several specific observational properties remain unexplained by any model, and that the sample is growing fast enough that new surprises arrive regularly. This is not a resolved problem. It is an active scientific frontier, and it has produced over 15 years of observation and analysis, some of the most detailed and most challenging anomalous signals in the history of radio astronomy. Chapter 2: The Anomaly from Proxima Centauri. Our nearest neighbour whispers something strange. In April 2021, a team of researchers at the Breakthrough Listen initiative, the most comprehensive, best-funded SETI program in history, published a paper in Nature Astronomy that sent a specific, careful shockwave through the scientific community. Not a sensational shockwave, not the kind that produces Hollywood press conferences and declarations of first contact. A precise, methodical, sober shockwave of the kind that propagates through a scientific community when someone publishes an anomaly that passes basic vetting but resists easy explanation. The paper described a narrowband radio signal detected at 982.002 MHz during observations of Proxima Centauri, the closest star to our solar system at 4.2 light-years distance. The signal, designated BLC1 for Breakthrough Listen Candidate 1, had properties that, taken together, placed it in a category of anomalies that SETI researchers take most seriously. Not because those properties are proof of anything extraordinary, but because they collectively represent a class of signal that is difficult to explain with any known natural or terrestrial source. Let's go through the properties carefully, because the specific combination of properties is what matters. First, the frequency, 982.002 MHz. Radio frequencies in this range are not typically associated with natural astrophysical emission processes. Stars don't produce narrowband continuous radio emission. Planets don't either. The molecular emission lines associated with interstellar chemistry occur at specific frequencies, but they are broad compared to this signal and don't fall at 982 MHz. The signal was not at a frequency predicted or expected from any natural source associated with Proxima Centauri. Second, the bandwidth. The signal was extremely narrowband. Its frequency spread was consistent with a drift-corrected bandwidth of less than a few hertz. Natural astronomical radio sources are broadband or produce emission at specific known spectral lines, which are much broader than this. An extremely narrowband signal is suggestive of a coherent emitter, something producing radio waves at a specific frequency rather than across a thermal or turbulent spectrum. Coherent emitters include masers and, notably, artificial radio transmitters. Third, the drift rate. The signal's frequency changed over time, drifting at a rate consistent with the Doppler shift produced by a source accelerating relative to the telescope, moving with a specific non-zero velocity profile. Terrestrial interference sources, satellites, aircraft, cell towers, military radar, typically produce signals at fixed frequencies or with drift rates consistent with known orbital mechanics. The drift rate of BLC1 was analysed against known satellite and aircraft trajectories and found to be inconsistent with all of them. It was also analysed against the known Doppler drift that would be produced by the Earth's rotation and its orbit around the Sun, the chirp that any truly cosmic signal would acquire because of the telescope's motion, and found to be roughly consistent with a sky-fixed source, though with uncertainties that make this analysis non-conclusive. Fourth, directionality. The signal appeared to be associated with the direction of Proxima Centauri in sky position. It appeared when Breakthrough Listen's Parkes telescope was pointed at Proxima Centauri and disappeared when the telescope was pointed away. This on-off behaviour with telescope pointing is a standard diagnostic for distinguishing real sky sources from instrumental artefacts. An artefact of the telescope's electronics would appear regardless of where the telescope was pointed, while a real sky source would follow the telescope's beam. These four properties, unusual frequency, extreme narrowband nature, non-terrestrial drift rate, and apparent sky directionality, are precisely the properties that SETI protocols designate as merit follow-up. The researchers, led by Shane Smith at Breakthrough Listen, with the collaboration of a large team including SETI Institute scientists and Breakthrough Listen's director Andrew Siemian, were careful in their characterization. The paper did not claim detection of extraterrestrial intelligence. It described an anomalous signal consistent with the properties SETI searches are designed to find, and noted that it had not been explained by any known natural or instrumental mechanism during the period of analysis prior to publication. The paper did not appear without context. BLC-1 was detected in data from April and May 2019. It was not immediately published. The team spent more than a year and a half attempting to understand it before publishing. During that time, researchers examined alternative explanations, searched for other instances of the signal in Breakthrough Listen's archive, attempted to replicate the detection with other telescopes, and consulted with radio frequency interference specialists. The fact that the paper was published despite this extended scrutiny, that the team could not explain it away, is significant. Breakthrough. Listen's protocols are designed to filter out false positives aggressively. When something survives those filters and makes it into print, it is genuinely anomalous. It is worth understanding what Breakthrough Listen's vetting process actually looks like in practice, because understanding the rigour of the filters gives weight to what passes through them. When a candidate signal is detected, the first step is to check whether it appears in the off-source data, the data collected when the telescope is pointed slightly away from the target source. If the signal appears both on-source and off-source, it is almost certainly terrestrial interference that illuminates the telescope regardless of pointing direction. BLC-1 appeared only on source. The second step is to check for the signal in the telescope's other beams. Modern radio telescopes often record data from multiple spatial regions simultaneously, and a signal from the sky will appear in one beam, while terrestrial interference will appear across multiple beams. The details of BLC-1's multi-beam behaviour were analysed and found to be consistent with a sky-directed source, though with the caveat that near-field interference patterns can sometimes mimic this behaviour. The third step is to check frequency against known RFI databases, catalogues of frequencies known to be contaminated by satellites, aircraft radar, cell towers, and other terrestrial emitters. BLC-1's frequency was not in any of these catalogues. It was also not found in any concurrent observation by other telescopes, which means it did not originate from a standard broadband interference source that would be visible globally. These are the filters. They are not perfect. Unusual interference events can sometimes mimic sky sources through complex near-field reflection and diffraction effects, but they are rigorous, and BLC-1 passed all of them. The publication represents the scientific community's honest acknowledgement that the signal resists ready explanation, not any claim about its origin. The community response was, appropriately, skeptical, but engaged. Several groups published papers examining alternative explanations. The most comprehensive came from researchers at the Netherlands Institute for Radio Astronomy, ASTRON, who identified a class of radio frequency interference from electronic devices that could, under specific circumstances, produce narrowband signals with drift rates and directional properties similar to BLC-1. Specifically, the researchers noted that certain interference patterns associated with electronics on or near the telescope could mimic the sky-directed behaviour if the electronics were themselves physically moved during the observation, or if they produced signals with a specific modulation pattern. Critically, this alternative explanation was not definitively demonstrated to apply to BLC-1. It was a class of explanation, a type of interference that could in principle produce similar features, not a specific identified source that was proven to have produced the BLC1 signal. The distinction matters enormously in the methodology of anomaly evaluation. Identifying a mechanism that could in principle produce a signal that looks like what you observed is not the same as demonstrating that this mechanism produced this specific signal. The history of astronomy is full of cases where proposed alternative explanations for anomalous signals were plausible in principle, but turned out to be wrong in the specific case. The requirement for anomaly resolution is not a natural explanation exists in principle, but this natural explanation is demonstrated to apply here. BLC1 has satisfied the first condition but not the second. It remains unresolved in the only sense that matters. We do not know what it was. As of the most recent published analyses, BLC1 has not been detected again from Proxima Centauri in follow-up observations. This is both reassuring and unsatisfying. Reassuring because a signal from a technological extraterrestrial source at Proxima Centauri would very likely be detectable in follow-up observations if it were an ongoing broadcast, and its non-redetection is therefore evidence against that interpretation. Unsatisfying because non-redetection is also consistent with a transient technical glitch, a one-time interference event, or a genuinely cosmic source that bursts only occasionally. The WOW signal was also never detected again. The absence of a second detection is ambiguous evidence about almost everything except the most sustained and powerful artificial broadcasts. There is a specific reason why Proxima Centauri as a source location is particularly interesting to SETI researchers, independent of BLC1 specifically. Proxima Centauri is a red dwarf star, with a confirmed planet, Proxima b, orbiting in its habitable zone. Proxima b's existence was announced in 2016, and subsequent analysis has refined our understanding of its properties. It is roughly Earth mass, orbits at a distance where liquid water could exist on its surface, and has been the subject of extensive study as one of the most accessible potentially habitable worlds in the galaxy. The fact that BLC1, whatever it is, appears to come from the direction of Proxima Centauri, the nearest star to Earth, which has a known potentially habitable planet, is not proof of anything. Directionality in radio telescope measurements is uncertain, and the beam is not perfectly sharp. But the coincidence is exactly the kind of specific location-relevant feature that elevates an anomaly from an interesting instrumental curiosity to something that warrants sustained scientific attention. The honest answer to what BLC1 is, we don't know, not we strongly suspect its interference and are waiting to confirm. We genuinely don't know. It passed the filters designed to reject known interference. It has a natural explanation that is plausible but unconfirmed, and it remains in the literature as an unresolved anomaly from the nearest star system to our own. Chapter 3, The Magneta That Played by the Wrong Rules. On April 28, 2020, a magneta in our own galaxy did something it was not supposed to do, and what it did tells us something specific and unsettling about the limits of our models, not just of magnetars, but of the entire physical regime of neutron stars and the most extreme magnetic fields in the universe. SGR 1935 + 2154, the soft gamma repeater that I mentioned briefly in the context of the galactic fast radio burst, had been known since 2014. It is approximately 30,000 light-years away, in the direction of the constellation Vulpecula, embedded in a supernova remnant that appears to be the relic of the explosion that created it. It is a magneta, a neutron star with a magnetic field of roughly 10 to the 14th to 10 to the 15th Gauss. For reference, Earth's surface magnetic field is about 0.5 Gauss. The strongest continuous magnetic fields achievable in terrestrial laboratories are around 45 Gauss continuously, and around 100 Gauss in pulsed experiments. A magnetar's field is more than 1 trillion times stronger than any magnetic field ever created by human technology. Magnetars are known to produce X-ray and gamma-ray bursts. They are the defining characteristic of the soft gamma repeater class. They produce these bursts through the catastrophic rearrangement of their magnetic fields, the cracking of their crystalline crusts under the stresses of those fields, the reconnection of magnetic field lines releasing enormous stored magnetic energy in seconds. They are, in the X-ray and gamma-ray sky, among the most violent transient sources known. What they are not supposed to do, what their models, in 2020 categorically did not predict was produce bright radio pulses. The electromagnetic emission from magnetars was understood to span the X-ray and gamma-ray domain. Radio emission from magnetars had been detected occasionally, but at very low levels and inconsistently, and in a way that was generally considered a secondary or marginal phenomenon. No one had predicted that a magnetar would produce a radio burst with the characteristics of an extragalactic fast radio burst. On April 28, 2020, SGR 1935 plus 2154 entered a period of elevated activity, producing multiple X-ray bursts. During this activity, 2 radio telescopes detected something that had never been seen before. CHIME, the Canadian telescope we discussed in the previous chapter, detected a bright radio burst. STARE-2, a radio transient monitor operated by Caltech, also detected the burst, independently, simultaneously. The 2 independent detections confirmed that the event was real and not an instrumental artifact. The radio burst had properties consistent with the known population of extragalactic fast radio bursts, except that it was much weaker, as expected from a source within our own galaxy, rather than billions of light-years away. If SGR 1935 plus 2154 were at the distance of a typical extragalactic FRB source, this burst would have been detected as an FRB. This was taken as strong evidence that at least some FRBs are produced by magnetars, the first direct association between a known galactic object type and the extragalactic phenomenon. The paper announcing this discovery was published in Nature in November 2020 and was immediately recognized as a landmark result. It was covered broadly in the astronomical press as a resolution of the FRB mystery. Magnetars are FRBs, problem solved, move on. But then the details started coming in, and the details revealed that the resolution was, at best, partial. The radio burst from SGR 1935 plus 2154 on April 28th was followed by a second burst on May 24th detected by the FAST telescope in China. The 2 bursts had different properties from each other and from the X-ray behaviour of the magnetar during the same periods. Most significantly, the correlation between X-ray activity and radio activity was not simple. During the intense X-ray bursting period in April, the radio burst occurred during one specific burst out of hundreds. During quiet periods when no X-ray bursts were detected, the radio emission sometimes appeared and sometimes didn't. A paper published in Nature Astronomy in 2022 by Lin, Zhang, and collaborators analysed 75 radio bursts detected by FAST from SGR 1935 plus 2154 during its 2020 to 2021 active periods. These bursts showed temporal and spectral structure, unlike anything in the theoretical models that had been proposed to explain FRBs. Some bursts had up to 5 distinct subpulses within a single event. The spectral shape of individual bursts changed from one burst to the next, in ways inconsistent with simple models of propagation through the magnetar's magnetosphere, and the radioactivity and X-ray activity seemed to be loosely correlated but not tightly coupled, suggesting that the radio emission mechanism was not simply a secondary byproduct of the magnetic crust cracking that produces X-ray bursts. There is a specific observation from this dataset that stands out as particularly difficult to explain. During one observational epoch, FAST detected radio bursts from SGR 1935 plus 2154 that had quasi-periodic structure, oscillations within the burst envelope with a period of approximately 2.4 milliseconds. A 2.4 millisecond period could correspond to the rotation period of the magnetar's emission beam. If the magnetar was rotating at about 417 rotations per second, but SGR 1935 plus 2154's known spin period, measured from its X-ray pulsations, is about 3.25 seconds, 417 rotations per second versus 0.31 rotations per second. These are not compatible. The quasi-periodic structure in the radio burst does not correspond to the magnetar's known rotation rate by any simple geometric model. This quasi-periodic fine structure has been interpreted by some as evidence for emission from the magnetar's magnetosphere at altitudes and geometries that don't directly reflect the rotation period, the equivalent of complex atmospheric oscillation modes rather than simple lighthouse beam rotation. This is physically plausible, but it is also physically complex in ways that are not well modelled and the specific 2.4 millisecond period has not been definitively explained. Beyond SGR 1935 plus 2154, the broader picture of radio emission from magnetars has continued to develop in unexpected directions. In 2022, the FAST telescope detected radio emission from a magnetar, SGR 1935 plus 2154, that appeared to have a drift pattern, the frequency of sub-pulses changing systematically within a burst, moving to lower frequencies over the course of milliseconds, that is reminiscent of the sad trombone drift seen in repeating extragalactic FRBs. This drift is predicted by some theoretical models involving the synchrotron maser mechanism, in which charged particles moving at relativistic speeds in a strong magnetic field produce coherent radio emission, whose frequency decreases as the particles lose energy. The observational match between the drift pattern of the galactic magnetar and the drift seen in some extragalactic FRBs is one of the strongest pieces of evidence for the magnetar-FRB connection. But the details of the drift rates, the sub-pulse spacings, and the burst energies still don't cleanly fit any single theoretical model. There is also the matter of XTEJ 1810-197, a different magnetar that in 2018 unexpectedly became radio bright after a decade of radio silence. Previously, XTEJ 1810-197 had been one of only 4 radio-emitting magnetars known, and it had gone radio quiet in 2008 after a period of activity. When it turned back on in late 2018, it was immediately studied by multiple radio telescopes worldwide. What they found was a magnetar whose radio emission had changed character. The bursts in 2018 to 2019 were more structured, more polarized, and showed finer temporal detail than the emission from the same source a decade earlier. The magnetar appeared to have evolved. Its emission geometry or magnetospheric structure had changed in ways that were not predicted by any pre-existing model of how magnetars change over time. A specific paper by Levin and collaborators in 2019 analysed the polarization properties of XTEJ 1810-197's revived radio emission, and found something that generated significant discussion. The polarization angle showed a specific, reproducible modulation over the course of the magnetar's rotation that was inconsistent with the standard rotating vector model used to describe pulsar polarization. The standard model assumes a fixed magnetic field geometry that rotates with the neutron star. XTEJ 1810-197's polarization behavior was not consistent with a fixed geometry. Either the magnetic field configuration was changing between rotations, on a timescale of seconds, or the emission was coming from a location in the magnetosphere where the standard geometric assumptions break down. The magnetar XTEJ 1810-197 adds a layer of strangeness to the radio magnetar story by demonstrating that these objects can be dormant, reactivate, and exhibit different emission properties upon reactivation than they had before. This implies that the magnetic field configuration of a magnetar, the structure that determines what kind of radio emission it produces, is not static. It evolves. And the evolution is not predictable in any detailed way from current models, because the interior physics of a neutron star, with its exotic equation of state and its quantum nuclear matter, is not computationally tractable to the level of detail that would allow specific predictions. What this means for the broader picture of anomalous signals is this: the class of objects most likely responsible for the majority of fast radio bursts, magnetars, is itself a class of objects whose behavior is not fully understood, whose radio emission mechanism is not fully modeled, and whose specific observable properties routinely produce features that current theories struggle to reproduce. The resolution of the FRB mystery into its magnetars is simultaneously true and insufficient. Magnetars can produce FRB-like emission. They cannot, in any current model, produce all the specific features of all the FRBs we have detected. The residual anomalies, the quasi-periodic substructures, the extreme polarization swings, the non-repeating population, the most energetic events at the bright end of the energy distribution, are still genuinely unresolved. There is also a hierarchy problem in the magnetar FRB explanation that is worth naming. The galactic FRB from SGR 1935 plus 2154, observed at its actual distance, had an energy roughly 1 million to 1 billion times lower than the brightest extragalactic FRBs. If extragalactic FRBs are produced by magnetars similar to SGR 1935 plus 2154, the energy gap must be explained by either extraordinary magnetar properties or specific environmental amplification effects. Some researchers have proposed that FRBs at the bright end of the energy distribution cannot be produced by any known magnetar using any known emission mechanism, and that the bright end of the FRB population may represent a qualitatively different physical process from the galactic event. In other words, there may be two FRB phenomena, one of which we understand moderately well, and one of which we do not understand at all. And underlying all of this is a physical regime. The behaviour of matter and electromagnetic fields at densities of 10 to the 14th power grams per cubic centimetre, and magnetic field strengths of 10 to the 15th power Gauss, that is not accessible to laboratory physics in any direct way. We cannot create these conditions. We can only observe their consequences from tens of thousands or billions of light years away, and try to infer the physics from the signals we receive. When those signals play by rules that our inferences don't predict, we are confronted with the limits of the only laboratory we have, the universe itself. Chapter 4: The Venus Phosphine Signal, a case study in how science handles the impossible. On September 14, 2020, a team of astronomers led by Jane Greaves at Cardiff University published a paper at SIS, Nature Astronomy, announcing the detection of phosphine in the atmosphere of Venus. The paper was measured in its language. It said the detection was unexpected, that known abiotic chemistry could not easily explain the observed concentration, and that the possibility of biological production could not be ruled out. It did not claim that Venus harboured life. It claimed that something was producing phosphine in Venus's atmosphere, that the known chemistry of that atmosphere could not account for. The reaction to the paper was, to put it mildly, dramatic. International media ran headlines about life on Venus. Scientists who had not been part of the research began publishing rapid response analyses. A congressional hearing touched on it, and within weeks, the field of planetary science was embroiled in one of the most contentious and instructive debates about anomalous signals in the history of the discipline. Let me explain the signal and why it was anomalous before explaining what happened next, because the story of what happened to the phosphine signal is as important as the signal itself for understanding how science processes claims of this kind. Phosphine, pH3, a molecule of one phosphorus atom bonded to 3 hydrogen atoms, is a gas that on Earth is produced primarily by biological processes. Certain anaerobic bacteria generate it as a metabolic byproduct, and by industrial activity. In the high-temperature, high-pressure environments of the gas giants Jupiter and Saturn, it is produced by chemical reactions driven by heat deep in the atmosphere. But Venus is neither a gas giant nor a biologically active world, or so we thought. Venus has a surface temperature of around 465 degrees Celsius, an atmosphere of 96.5% carbon dioxide, sulfuric acid clouds, and atmospheric chemistry that has been modelled in detail by decades of research. The equilibrium chemistry of Venus's atmosphere produces vanishingly small amounts of phosphine, because the oxidizing conditions rapidly destroy it. The predicted abundance is parts per trillion, far below detectability. Greaves and her team, using data from the James Clerk Maxwell Telescope in Hawaii and subsequently the ALMA Interferometer Array in Chile, claim to detect phosphine at a concentration of around 20 parts per billion, several orders of magnitude above any prediction from known abiotic chemistry. This was the anomaly, a molecule present at concentrations far exceeding what the known physics and chemistry of the Venusian atmosphere should allow, with no obvious non-biological source. The announcement ignited an immediate and intense scientific debate. Within days, researchers began questioning whether the signal was real, and the questioning was directed not at the biology versus abiotic chemistry debate that came later, but at the more fundamental question of whether the detection itself was valid. The ALMA data, it turned out, had been calibrated using an incorrect version of the telescope's spectral response function. When the calibration was corrected, the apparent phosphine signal weakened substantially. A reanalysis published in November 2020 by researchers at the National Radio Astronomy Observatory suggested that the correct phosphine abundance, after recalibration, might be substantially lower than the originally claimed 20 parts per billion, perhaps as low as 1 to 4 parts per billion, or possibly consistent with 0. Greaves' team reanalyzed their data accepted some of the calibration corrections and revised their estimate downward while maintaining that a detection above the noise floor remained. Other groups disagreed. Papers were published on multiple sides. The Journal of Geophysical Research. Planets published a comprehensive reanalysis in 2021 that concluded the data were consistent with a phosphine detection at lower concentrations than originally claimed, and that the signal was probably real but substantially weaker than initially reported. But then a second, subtler controversy emerged. Even accepting a detection of phosphine at some concentration, what does it mean? The initial claim was that known abiotic chemistry could not explain it. But how confident were we in our models of Venus's atmospheric chemistry? Researchers at the Massachusetts Institute of Technology and elsewhere began systematically examining every known abiotic chemical pathway for phosphine production in Venus-like conditions: lightning, volcanic activity, photochemical reactions in the upper atmosphere, reactions with minerals transported from the surface, exotic chemistry at the interface between the cloud layers and the upper atmosphere. A 2021 paper by Paul Rimmer and colleagues at Cambridge systematically evaluated every known phosphorus chemistry pathway in Venus conditions and confirmed that the equilibrium chemistry of the known Venusian atmosphere could not produce phosphine at the claimed concentrations. This was not a trivial calculation. The Venusian atmosphere contains over 24 chemical species in complex reaction networks, and the evaluation required building a comprehensive atmospheric chemistry model. The conclusion was that life was not ruled in, but known abiotic chemistry was genuinely challenged. A separate paper the same year proposed that volcanic eruptions could inject phosphine from the deep crust into the upper atmosphere if specific phosphid minerals were present in Venus's interior and if the volcanic activity were intense enough. This proposal was not implausible. We have limited direct knowledge of Venus's crustal composition, but critics noted that the required volcanic flux of phosphide-rich material would be substantially larger than anything observed on Earth or inferred for Venus. The phosphine debate also illuminated a broader scientific question about Venus's clouds that had been lurking at the fringes of planetary science for decades. Carl Sagan and Harold Morowitz, in a 1967 paper in Nature, had proposed that the sulfuric acid clouds of Venus at altitudes between 48 and 60 kilometers, where temperatures are between 0 degrees Celsius and 70 degrees Celsius, and pressures are between 0.4 and 2 atmospheres, conditions broadly similar to Earth's lower atmosphere, might be habitable for aerial microbial life. The clouds contain water, albeit at very low concentrations, chemical energy gradients, and the right temperature and pressure range. Sagan's proposal was speculative but not physically ridiculous. The phosphine detection, coming more than 50 years after that speculative proposal, was interpreted by some researchers as indirect support for aerial biosphere models. Not proof, far from it. But if microorganisms were somehow living in Venus's cloud layers, metabolically processing sulfur and other available compounds, they might plausibly produce phosphine as a byproduct. The idea gained enough traction that a dedicated mission concept, the Venus Life Finder, was proposed as a private space mission, specifically designed to look for aerial life in Venus's clouds, with instruments including a droplet impactor capable of analysing individual cloud particles for complex organics and chiral molecules. Whether the Venus Life Finder is ever funded and flown remains uncertain, but its emergence as a serious mission concept, with participation from researchers at MIT and other institutions, represents the degree to which the phosphine anomaly, even in its weakened post-recalibration form, has elevated the question of Venusian life from purely speculative to scientifically worth pursuing with dedicated instrumentation. The Venus phosphine story is, as of 2025, unresolved. There is likely some phosphine in Venus's atmosphere at concentrations somewhat above the equilibrium prediction. Whether it is significantly above equilibrium, and what produces it, remains debated. The biological hypothesis has not been confirmed. The abiotic alternative explanations have not been definitively ruled in either. What the story illustrates, and why it belongs in a discussion of anomalous signals, is the process by which the scientific community handles a claim that sits at the intersection of anomalous instrument data and extraordinary implications. The community did not immediately accept the detection. It did not immediately dismiss it. It scrutinized the calibration, revised the data reduction, explored alternative explanations, published competing analyses, and arrived at a state of informed uncertainty that is more precise than the original claim but still genuinely unresolved. This is science working correctly. It is uncomfortable. It produces years of debate rather than clean answers, but it is the only honest way to handle a signal that shouldn't exist. Chapter 5. Boyajian's Star. When a star decided to break physics. In 2015, a paper appeared in the monthly notices of the Royal Astronomical Society that began attracting attention, in ways unusual for a routine light curve analysis paper. Its title was unremarkable: Planet Hunters X, KIC 8462852, Where's the Fleex? But its content was anything but routine, and the star it described, now known as Boyajian's Star after the paper's lead author, Tabitha Boyajian, became the subject of more scientific and popular discussion than any single star since pulsars. KIC 8462852 is an F-type main sequence star approximately 1,470 light-years away. It is somewhat hotter and somewhat larger than the Sun. In the data from NASA's Kepler Space Telescope, which monitored it continuously for 4 years between 2009 and 2013, it showed a light curve unlike anything in Kepler's catalogue of 150,000 observed stars. Most stars that show periodic dips in brightness, in Kepler data, show the characteristic symmetric repeated dip pattern of a transiting planet, a planet whose orbit carries it across the face of the star once per orbital period, blocking a small fixed fraction of the starlight. KIC 8462852 showed something different. Its dips were aperiodic, occurring at irregular intervals, not on a fixed schedule. They were asymmetric. The ingress and egress profiles did not mirror each other the way a circular planet transit would. They were deep, at times blocking up to 22% of the star's light, far more than any known planet could produce, and they were complex. During the largest dips, the light curve showed multiple subdips within a single event, as though multiple occulting structures were passing in front of the star simultaneously. The paper's title, Where's the Flux?, was a deliberately informal acknowledgement that the analysis team, which included both professional astronomers and volunteers from the Planet Hunters Citizen Science Project, genuinely did not know what was causing these dips. They presented the data and the known exclusions. The dips were not consistent with a planetary transit, not consistent with instrumental artifacts. The same dips appeared in multiple instrument channels, not consistent with stellar variability of any known type for this class of star. They were consistent with the transit of a swarm of large, irregularly shaped, non-spherical objects passing in front of the star. The paper listed the candidate explanations in order of plausibility. Near the bottom of the list, explicitly flagged as the least likely but not impossible explanation, was the possibility of artificial megastructures in orbit around the star. A Dyson sphere or a partial Dyson swarm under construction, a structure built by an advanced civilization to capture stellar energy, would, if its panels and components were incompletely assembled, block starlight in exactly the kind of irregular, asymmetric, variable pattern observed. The paper was honest about how improbable this explanation was, but it was honest also about the fact that none of the more plausible natural explanations fully accounted for the data. The public and media response was predictable. Alien megastructures. The scientific response was more measured but equally engaged. Within months, dozens of papers appeared proposing natural explanations. The most discussed was a swarm of comets or comet fragments, disrupted from the outer reaches of the star's system and falling inward on a range of orbits, collectively blocking starlight in a variable, irregular pattern. The comet swarm model had appeal. It was physically plausible, it could explain the aperiodicity and the asymmetry, and it didn't require exotic physics. But detailed modelling showed that the sheer number of comets required to block 22% of the starlight was extraordinarily large. Estimates ranged in the millions to hundreds of millions of comets, and the specific profile of the largest dips was not well reproduced by simple comet swarm models. Then, in 2016, a different and more troubling anomaly was identified. Astronomer Bradley Schaefer analysed photographic plates from the DASH survey, a decades-long project digitising historical photographic plates of the sky, taken between 1890 and 1989, and reported that KIC 8462852 had dimmed by about 0.16 magnitudes, over the full century of observations, a century-long secular dimming at a rate of about 0.165 magnitudes per century. Stars of this type don't do this. F-type main sequence stars are stable on timescales of millions of years. A dimming of this magnitude over 1 century has no obvious natural stellar explanation. Schaefer's result was contested. Several groups reanalyzed the DASH data and found smaller or negligible long-term trends, attributing Schaefer's result to calibration issues with the oldest photographic plates. The community divided. Some accepted that there was genuine secular dimming, others did not. The disagreement was about calibration uncertainty in century-old photographic data, which is genuinely difficult to resolve, but then, in 2018, a definitive result arrived from a different direction. The Astronomical Journal published a paper by Boyajian herself, with a large collaboration of observers, reporting the results of a photometric monitoring campaign that had captured several new dipping events in real time between 2016 and 2018. These new dips allowed something that the Kepler data could not provide: multi-wavelength light curves measuring the star's brightness simultaneously in different colors: ultraviolet, blue, green, red, infrared. The wavelength dependence of the dips was the key finding. If the dimming was caused by opaque objects, solid bodies like comets or spacecraft panels, the dimming would be the same in all wavelengths. Opaque objects block all light equally regardless of color. If the dimming was caused by dust, small particles whose size is comparable to or smaller than the wavelength of light, the dimming would be wavelength dependent, with bluer light being dimmed more than redder light, because small particles scatter and absorb blue light more efficiently than red. This is the same phenomenon that makes sunsets red on Earth. Small atmospheric particles scatter the blue component of sunlight more than the red. The 2018 dipping events showed wavelength-dependent dimming. Bluer wavelengths were dimmed more than redder wavelengths. This was compelling evidence that the occulting material was fine dust, not solid objects. The dust interpretation pointed toward comets, which release dust as they sublimate in the inner solar system, and away from solid megastructures. This result was widely interpreted as resolving the mystery in favor of the natural explanation. Comets, or something producing a dust swarm, were causing the dips. The megastructure hypothesis appeared to be ruled out. But the story doesn't end there. The dust interpretation resolves the short timescale dips, but it doesn't obviously resolve the century-long secular dimming that Schaefer's analysis suggested, if that dimming is real. And it doesn't explain the secular infrared excess that has been reported by some analyses. An elevated infrared brightness consistent with warm dust orbiting the star at a specific temperature, which would require a sustained reservoir of dust being continuously replenished rather than a single comet disruption event. The dust interpretation answers one question while leaving others open. As of 2025, the current best explanation for KIC 8462852 is an ongoing comet disruption event, probably involving a recently shattered large body in the outer planetary system. But the secular dimming remains contested. The infrared excess interpretation is unresolved, and the specific quantitative details of the dip morphology, particularly the largest events, have not been cleanly reproduced by any published physical model. Boyajian's star represents a class of anomaly that is different from FRBs or BLC1. It is an anomaly that has been partially explained, where the partial explanation raised new anomalies and where the resolution of the most extraordinary claim, megastructures, does not constitute a complete explanation of all the observed features. This is common in science. Anomalies rarely yield to a single explanation that cleanly accounts for every data point. What matters is whether the residual unexplained features are small enough to attribute to measurement uncertainty and model simplification, or whether they represent a genuine gap. In the case of Boyajian's star, the residual gaps are not trivially small. They are being actively studied. Chapter 6: The 2023 Radio Signals and the New Anomaly Season. The scientific anomaly landscape has shifted noticeably in the last 2 to 3 years, with several new detections entering the literature that are generating sustained debate. These are not cold cases from the archive. They are recent, current, and in some cases actively being studied with new observations as this script is written. The periodic radio transient from the Galactic Center, in January 2023, A paper published in Nature Astronomy by Ziteng Wang and collaborators at the University of Sydney announced the discovery of a radio source, designated Gleam X J16275-9.5-5-23504.3, that emitted radio pulses for approximately 60 seconds, once every 18.18 minutes. The source was detected in data from the Murchison Wide Field Array in Australia, active during 2018. Periodic radio transients are not unprecedented. Pulsars pulse periodically, and other classes of variable radio source are known. What made Gleam XJ 1627-59.5-5-2350-4.3 anomalous was its period, 18.18 minutes. No known rotating astrophysical object is known to produce coherent radio emission at such a slow rotation rate. Pulsars rotate much faster. The slowest known radio pulsar before this discovery had a period of about 11.8 seconds, still more than 90 times faster than this new source. Neutron stars with such slow rotation rates should not, according to standard models of neutron star evolution, be capable of producing the radio emission process. As a neutron star slows down, it crosses a theoretical death line, a threshold in the rotation period and magnetic field strength parameter space, below which the pulsar emission mechanism can no longer operate. A period of 18.18 minutes is well below the death line for any standard neutron star model. The discovery paper acknowledged this explicitly. The nature of Gleam XJ 1627-59.5-5-23504.3 is not immediately obvious, it stated, in the careful language of a team aware that their result contradicts established theory. They proposed that it might be a white dwarf, a much less dense stellar remnant that can rotate slowly without crossing the radio death line, or an ultra-long period magnetar, a magnetar spinning down to periods far longer than previously known examples. The white dwarf hypothesis is physically interesting. Some white dwarfs are known to produce radio emission in binary star systems through specific interaction mechanisms, but the emission characteristics of Gleam XJ 16275-5-52350-4.3, high degree of linear polarization, high brightness temperature, pulse profile structure, are not consistent with known white dwarf radio emission mechanisms. The ultra-long period magnetar hypothesis is similarly physically interesting, but requires extending magnetar models into a regime where the emission mechanism is not well established. In December 2022, before the paper's publication, another ultra-long period transient was reported, GPMJ 1839-10, detected by multiple radio telescopes and found to have a period of 21 minutes. Like Gleam X, GPMJ 1839-10 produced pulses of high linear polarization with complex subpulse structure. Unlike Gleam X, GPMJ 1839-10 was found in archival data going back to 1988, meaning this source had been active for at least 35 years, which essentially rules out any model involving a catastrophic event that produced a single brief phase of activity. The two detections together established that ultra-long period radio transients are a real class of object, not a single anomalous event. But what they are physically, what rotates or oscillates on 18 to 21 minute periods and produces coherent, highly polarized radio emission, is not known. No published model fully accounts for all their properties. The theoretical discussion is active, vigorous, and has not converged. A third member of this class, ASCAP J 193505.1+21484.1.0, was reported in 2023 in Nature Astronomy. Its period is approximately 54 minutes. This source has additional unusual properties. Its circular polarization fraction is variable between pulses, and during some activity cycles it shows 100% circular polarization, while during others it shows predominantly linear polarization. The rapid switching between polarization states within a single source is deeply unusual and has no clear physical model. The growing catalogue of ultra-long period radio transients represents one of the most active anomaly categories in observational radio astronomy in 2024. The instruments finding them, Meerkat in South Africa, ASCAP in Australia, the Murchison Wide Field Array, are all relatively new and are conducting wide-field time-domain surveys with sensitivity levels that were not available to previous surveys. The most conservative interpretation is that these sources represent a previously unknown population of known objects, white dwarfs, or exotic neutron stars, emitting through unknown mechanisms. But unknown mechanism is doing a lot of work in that sentence. The 2023 fast detection of an anomalous signal from the NGC 6946 direction. In late 2023, a preprint circulated within the radio astronomy community describing a set of anomalous radio pulses detected by FAST during a survey pointing toward NGC 6946, a galaxy about 22 million light-years away. The pulses had properties superficially similar to FRBs, but with dispersion measures that, if they reflected the true distance to the source, were inconsistent with the known electron density models for that line of sight. The apparent source could not be straightforwardly assigned to any known distance or object class. This detection had not, as of the time of this script, been published in a peer-reviewed journal, and its status was that of a candidate signal under active analysis. I include it not to claim significance for an unreviewed result, but because it illustrates a broader point. The discovery phase for anomalous radio signals is now operating faster than the publication cycle. FAST produces so much data, with such sensitivity, that the community is regularly encountering signals that resist immediate classification and that require weeks to months of analysis before a disposition, real or artifact known, class or unknown, can be assigned with confidence. This is new. It represents a change in the nature of the anomaly landscape. In the era of the WOW signal, anomalous signals were rare enough that each one could receive sustained individual attention. In the era of FAST and CHIME and the SKA, anomalous signals are frequent enough that the community must develop systematic pipelines for their classification, and the backlog of candidates under analysis at any given time is substantial. The 2022 Decameter radio emission from Uranus. In a less publicised but scientifically significant result, a 2022 paper in Nature Astronomy by Zarka and collaborators reported the detection of Decameter radio emission from Uranus, radio waves in the wavelength range of tens of meters, corresponding to frequencies of a few tens of megahertz. This was the first confirmed detection of this type of emission from Uranus, and its properties were unexpected. Ice giants, Uranus and Neptune, were predicted to produce radio emission from their magnetospheres as Jupiter and Saturn do. Jupiter's Decameter emission is well studied and understood in terms of electron-cyclotron maser instability in Jupiter's auroral regions. But Uranus's magnetosphere is bizarre by planetary standards. Its magnetic axis is tilted 59 degrees from its rotation axis and offset from the planet's centre by about a third of the planet's radius. This geometry produces a magnetosphere that wobbles and tumbles as the planet rotates, in ways that are not well modelled by the frameworks developed for Jupiter and Saturn. The detected Uranian radio emission was stronger than pre-existing models had predicted. Its spectral properties and temporal variability were qualitatively consistent with electron-cyclotron maser processes, but quantitatively different from what the known magnetospheric models would compute. The energy budget implied by the emission required either a more powerful electron acceleration process than had been modelled, or a more efficient emission geometry, or both. This is not a SETI candidate signal. Uranus is firmly a solar system object of known natural origin. But the fact that a planet in our own solar system produces radio emission that exceeds its modelled predictions is a reminder that even in the most locally accessible and most intensively studied planetary system, our models leave gaps. When those gaps occur at Jupiter or Saturn, which have been extensively observed, they are quickly explained. When they occur at Uranus, which has been visited by only one spacecraft, Voyager 2 in 1986, they have the potential to reveal something genuinely new about the physics of magnetospheres in a physical regime that is not well sampled. Chapter 7. What the signals mean. Collectively, we have now surveyed a range of anomalous signals spanning a decade of observational astronomy, the fast radio burst phenomenon and its magnetar connection, BLC-1 from the direction of Proxima Centauri, the galactic magnetar's rule-breaking radio emission, the Venus-Phosphine controversy, the Boyajian star puzzle, the ultra-long period transients, and the most recent detections from FAST and the Southern Sky surveys. Taken individually, each of these signals has a working natural explanation or a class of natural explanations that is plausible. Magnetars probably produce most FRBs. BLC1 is probably an instrumental artifact of a type not yet identified. The dimming of Boyajian's star is probably caused by a comet swarm. The ultra-long period transients are probably novel manifestations of known object types. The word probably does a lot of work in each of these sentences, and the probably in each case is based on incomplete evidence pointing toward the natural explanation rather than fully establishing it. What does it mean, collectively, that so many anomalous signals have accumulated in the literature within a single decade? There are 3 possible readings, and a careful analysis requires holding all 3 simultaneously. The first reading is, instrumentation has improved dramatically, and we are now detecting a broader range of natural phenomena that existed before but were invisible to previous instruments. CHIME, FAST, MEERKAT, the MWA, ESCAPE. These instruments are qualitatively more sensitive and more comprehensive in their sky coverage than anything that existed before 2015. They are finding signals that were always there but that older equipment couldn't detect. The anomalies accumulate because the discovery space has expanded, not because the universe has become more anomalous. This is the most conservative reading and is almost certainly partially true. The second reading is, our models of certain extreme physical processes, neutron star magnetospheres, FRB emission mechanisms, magnetic field configurations around compact objects, are more incomplete than we previously appreciated. The anomalies accumulate because we are now getting high-fidelity data from physical regimes that were previously undersampled, and the data is revealing that our models, good as they are, have specific gaps. This is also almost certainly partially true, and it is the most scientifically productive reading because it drives model development. The third reading, the one that is most uncomfortable but most important to hold as a possibility, is some fraction of anomalous signals represent phenomena that have no explanation in the current physical framework. Not exotic physics, not unknown object types, phenomena that require a conceptual revision of some kind, a new mechanism, a new object class, a new physical process, whose specific nature we cannot predict in advance because our current framework doesn't contain it. This is also almost certainly partially true at some level, because the history of astronomy is the history of just this kind of revision. There is a specific property of the current anomaly landscape that makes the third reading more plausible than it might otherwise be. The anomalies are not uniformly distributed. They cluster in specific physical regimes. The fast radio burst anomalies cluster in the regime of neutron stars with extreme magnetic fields. The ultra-long period transients cluster in the regime of slowly rotating compact objects. The SETI candidate signals cluster in the regime of narrow-band radio emission from specific sky locations. These are not random-looking anomalies scattered uniformly across all domains of astronomy. They are concentrated in the domains where our physics is least well tested and our models most simplified. This clustering is itself informative. It suggests that whatever drives these anomalies, whether incomplete models, observational limitations, or genuinely new physics, operates in specific physical regimes and not uniformly across all of astronomy. The regimes in question, extreme magnetism, extreme density, extreme compactness, are precisely the regimes where quantum effects, general relativistic effects, and strong field electrodynamics interact in ways that are not computationally tractable from first principles. We simplify, we model, we extrapolate, and where we extrapolate the most, the anomalies accumulate. On September 14, 2020, a team of astronomers led by Jane Greaves at Cardiff University published a paper in Nature Astronomy announcing the detection of phosphine in the atmosphere of Venus. The paper was measured in its language. It said the detection was unexpected, that known abiotic chemistry could not easily explain the observed concentration, and that the possibility of biological production could not be ruled out. It did not claim that Venus harboured life. It claimed that something was producing phosphine in Venus's atmosphere that the known chemistry of that atmosphere could not account for. The reaction to the paper was, to put it mildly, dramatic. International media ran headlines about life on Venus. Scientists who had not been part of the research began publishing rapid response analyses. A congressional hearing touched on it. And within weeks, the field of planetary science was embroiled in one of the most contentious and instructive debates about anomalous signals in the history of the discipline. Let me explain the signal and why it was anomalous before explaining what happened next, because the story of what happened to the phosphine signal is as important as the signal itself for understanding how science processes claims of this kind. Phosphine, pH3, a molecule of one phosphorus atom bonded to 3 hydrogen atoms, is a gas that on Earth is produced primarily by biological processes, certain anaerobic bacteria generate it as a metabolic byproduct, and by industrial activity. In the high-temperature, high-pressure environments of the gas giants, Jupiter and Saturn, it is produced by chemical reactions driven by heat deep in the atmosphere. But Venus is neither a gas giant nor a biologically active world, or so we thought. Venus has a surface temperature of around 465 degrees Celsius, an atmosphere of 96.5% carbon dioxide, sulfuric acid clouds, and atmospheric chemistry that has been modelled in detail by decades of research. The equilibrium chemistry of Venus's atmosphere produces vanishingly small amounts of phosphine because the oxidizing conditions rapidly destroy it. The predicted abundance is parts per trillion, far below detectability. Greaves and her team, using data from the James Clerk Maxwell Telescope in Hawaii and subsequently the ALMA Interferometer Array in Chile, claim to detect phosphine at a concentration of around 20 parts per billion, several orders of magnitude above any prediction from known abiotic chemistry. This was the anomaly, a molecule present at concentrations far exceeding what the known physics and chemistry of the Venusian atmosphere should allow, with no obvious non-biological source. The announcement ignited an immediate and intense scientific debate. Within days, researchers began questioning whether the signal was real, and the questioning was directed not at the biology versus abiotic chemistry debate that came later, but at the more fundamental question of whether the detection itself was valid. The ALMA data, it turned out, had been calibrated using an incorrect version of the telescope's spectral response function. When the calibration was corrected, the apparent phosphine signal weakened substantially. A reanalysis published in November 2020 by researchers at the National Radio Astronomy Observatory suggested that the correct phosphine abundance, after recalibration, might be substantially lower than the originally claimed 20 parts per billion, perhaps as low as 1 to 4 parts per billion, or possibly consistent with 0. Greaves's team reanalyzed their data, accepted some of the calibration corrections, and revised their estimate downward while maintaining that detection above the noise floor remained. Other groups disagreed. Papers were published on multiple sides. The Journal of Geophysical Research, Planets published a comprehensive reanalysis in 2021 that concluded the data were consistent with a phosphine detection at lower concentrations than originally claimed, and that the signal was probably real, but substantially weaker than initially reported. But then a second, subtler controversy emerged. Even accepting a detection of phosphine at some concentration, what does it mean? The initial claim was that known abiotic chemistry could not explain it. But how confident were we in our models of Venus's atmospheric chemistry? Researchers at the Massachusetts Institute of Technology and elsewhere began systematically examining every known abiotic chemical pathway for phosphine production in Venus-like conditions. Lightning, volcanic activity, photochemical reactions in the upper atmosphere, reactions with minerals transported from the surface, exotic chemistry at the interface between the cloud layers and the upper atmosphere. A 2021 paper by Paul Rimmer and colleagues at Cambridge systematically evaluated every known phosphorus chemistry pathway in Venus conditions and confirmed that the equilibrium chemistry of the known Venusian atmosphere could not produce phosphine at the claimed concentrations. This was not a trivial calculation. The Venusian atmosphere contains over 24 chemical species and complex reaction networks, and the evaluation required building a comprehensive atmospheric chemistry model. The conclusion was that life was not ruled in, but known abiotic chemistry was genuinely challenged. A separate paper the same year proposed that volcanic eruptions could inject phosphine from the deep crust into the upper atmosphere if specific phosphide minerals were present in Venus's interior and if the volcanic activity were intense enough. This proposal was not implausible. We have limited direct knowledge of Venus's crustal composition, but critics noted that the required volcanic flux of phosphide-rich material would be substantially larger than anything observed on Earth or inferred for Venus. The phosphine debate also illuminated a broader scientific question about Venus's clouds that had been lurking at the fringes of planetary science for decades. Carl Sagan and Harold Morowitz, in a 1967 paper in Nature, had proposed that the sulfuric acid clouds of Venus at altitudes between 48 and 60 kilometers where temperatures are between 0 degrees Celsius and 70 degrees Celsius, and pressures are between 0.4 and 2 atmospheres, conditions broadly similar to Earth's lower atmosphere, might be habitable for aerial microbial life. The clouds contain water, albeit at very low concentrations, chemical energy gradients, and the right temperature and pressure range. Sagan's proposal was speculative, but not physically ridiculous. The phosphine detection, coming more than 50 years after that speculative proposal, was interpreted by some researchers as indirect support for aerial biosphere models. Not proof, far from it. But if microorganisms were somehow living in Venus's cloud layers, metabolically processing sulfur and other available compounds, they might plausibly produce phosphine as a byproduct. The idea gained enough traction that a dedicated mission concept, the Venus Life Finder, was proposed as a private space mission, specifically designed to look for aerial life in Venus's clouds, with instruments including a droplet impactor capable of analysing individual cloud particles for complex organics and chiral molecules. Whether the Venus Life Finder is ever funded and flown remains uncertain, but its emergence as a serious mission concept, with participation from researchers at MIT and other institutions, represents the degree to which the phosphine anomaly, even in its weakened post-recalibration form, has elevated the question of Venusian life from purely speculative to scientifically worth pursuing with dedicated instrumentation. The Venus phosphine story is, as of 2025, unresolved. There is likely some phosphine in Venus's atmosphere at concentrations somewhat above the equilibrium prediction. Whether it is significantly above equilibrium and what produces it remains debated. The biological hypothesis has not been confirmed. The abiotic alternative explanations have not been definitively ruled in either. What the story illustrates, and why it belongs in a discussion of anomalous signals, is the process by which the scientific community handles a claim that sits at the intersection of anomalous instrument data and extraordinary implications. The community did not immediately accept the detection. It did not immediately dismiss it. It scrutinized the calibration, revised the data reduction, explored alternative explanations, published competing analyses, and arrived at a state of informed uncertainty that is more precise than the original claim but still genuinely unresolved. This is science working correctly. It is uncomfortable. It produces years of debate rather than clean answers. But it is the only honest way to handle a signal that shouldn't exist. Conclusion. We began with Jerry Eman sitting at a desk in 1977, circling a sequence of letters in a computer printout and writing "wow" in the margin. That single moment of a scientist recognizing that data was telling him something he didn't understand has a specific and irreplaceable quality. The quality of genuine surprise, genuine uncertainty, genuine openness to the possibility that the universe is doing something it isn't supposed to do. 47 years later, we have instruments 1,000 times more sensitive, collecting data 1,000,000 times more rapidly, scanning sky areas that would have taken decades with 1977-era telescopes. We have an entire field of radio transient astronomy that didn't exist in 1977. We have dedicated SETI programs funded at a level Eman could not have imagined. We have the FAST telescope in China, with its 500-meter aperture, generating datasets so large that the anomaly triage problem, the problem of identifying which signals warrant sustained attention, has become a significant engineering and computational challenge in its own right. And we still have unexplained signals, the FRBs that exceed every known energy scale, the galactic magnetar that rotates at 0.31 Hz and emits radio bursts with quasi-periodic structure at 417 Hz. The signal from the direction of Proxima Centauri that passed every interference filter and has never recurred. The ultra-long period transients that rotate every 18 to 54 minutes and cross every theoretical deathline for coherent radio emission. The dimming of Boyajian's star, partially explained by dust but not fully accounted for by any published model. The phosphine on Venus, possibly overestimated but not fully explained by any known abiotic chemistry at any plausible concentration. None of these signals individually compels an extraordinary conclusion. Each one has a natural explanation that is plausible, sometimes more than plausible, sometimes effectively demonstrated, and the appropriate scientific response to each is continued analysis, deeper observations, better models, and patience. Most anomalies resolve. The history of astronomy guarantees this. The history of astronomy is largely a history of anomalies resolving into understood phenomena, with a small fraction resolving into new physics. But most anomalies resolve is not all anomalies resolve, and natural explanation is plausible is not natural explanation is confirmed. The distinction between those two statements is where science lives, in the space between tentative understanding and certainty, in the ongoing process of accumulating evidence until one explanation is so well supported and all others so thoroughly excluded that certainty becomes the appropriate word. We are not at certainty for any of the signals discussed in this video. We are at various stages of incomplete explanation, ranging from probably natural but details unresolved, to genuinely puzzling with multiple competing models and no clear winner. That range of partial explanations is not a failure of the scientific process. It is the scientific process, operating honestly on a universe that yields its secrets slowly. What the accumulated signals of the last decade do tell us, what they collectively demonstrate beyond any specific candidate explanation, is that the universe is more observationally diverse than our models have captured, and that the instruments we are now deploying are sensitive enough to detect phenomena in physical regimes where our models are incomplete. This is a gift, scientifically. Every anomaly is a pointing hand, indicating a gap between what we understand and what is. Every unresolved signal is an open question with a real answer that we have not yet found. The answer might be a new emission mechanism for magnetars. It might be a new class of compact object. It might be industrial RFI reflected off an atmospheric layer in a way not previously modelled. It might be the chemistry of an extreme environment producing molecules that our solar system analogues don't generate. It might be something else, something outside every category we currently have names for. The signals are real, the detections are documented, the publications are peer-reviewed and reproducible, the anomalies are genuine, whatever they turn out to be. However the explanations eventually arrive and however ordinary or extraordinary they prove to be, the act of taking them seriously, studying them rigorously, resisting both the impulse to overclaim and the impulse to dismiss, is the best thing science has ever done and the only honest response to a universe that keeps telling us things we weren't expecting to hear. Jerry Amon circled a signal and wrote one word. He was right to be surprised.